Good morning. It's Angie with Angie's Beyond the Lecture, and I'm taking a walk back in time to a worksheet that I posted about 3 weeks ago. It's a free worksheet out on Patreon, and it's just a single problem worksheet here. And I want to go over a couple things when it comes to math and more specifically algebra. Now, before we move forward, again, my name is Angie. I'm with Angie's Beyond the Lecture. I've been a tutor for nearly 2 decades, mainly working with the STEM subjects like chemistry and biology and working with high school students and college. And as a matter of fact, I was a college tutor over at Collin College, just north of Dallas. So anyway, let's dive right in here. Now, you'll notice the first page of this worksheet has the initial rate data. This is experimental data. Remember, with rate laws, we need experimental data. We can't just pull that from the balanced chemical reaction equation. All right, so here we go. We have 3 runs here. We have concentrations listed and initial rates in concentration per second or molarity per second. And I have the work written out down here. And I wanted to go over, I'm just going to take a little scroll down here. Now, I broke this down into 2 steps. We have 2 species to be concerned about here. We have the ClO2 or the hypo, I believe that's hypo. No, sorry, that's chloride. Yeah, that's the chloride ion and the hydroxide ion in this particular situation. And basically, the first thing you really need to do here is set up your generic rate laws for run 1 and run 2. So notice, and that's going to be right here. So we have rate 1, we have our constant K, which we don't know, we're not given that. And then we have our ClO2 to the X power, and then OH to the Y power. And these subscripts right here just demonstrate that it's in run 1. Ditto for rate 2, we just take our rate constant K times the ClO2 to the X power, or unknown X power, and then OH or hydroxide to the Y power, and we use the subscripts just to note that this is run 2. You could actually, write out run 1, run 2, maybe to not get your subscripts confused. That's another way you could do it. Now, the key here is that we're trying to solve for unknown exponents. So that could be sort of tricky. You recall, for instance, algebra 2, we used logs, if we had an unknown exponent here to solve for. But here we can actually, because we have some data here that we can fill in the gaps with the bases, right? The ClO2s and the OHs, we can actually make this a bit easier now. So if we scroll down here, we're gonna divide these 2 equations here, and it's important. I'm going to demonstrate, I'm going to erase that here. So I'm going to demonstrate the key here is that hopefully you realize, for instance, that we do know, right? We did take rate 2 and rate 1 and rate 2 together, and we're going to divide them because we know when I substitute ClO2 in runs 1 and 2, they're both the same. They're both at the 0.0010 molarity. They're just going to cancel, okay? And then the K's will cancel. What's left standing? What's left standing, you ask? It's just going to be these 2 species right here. That X is a little bit close to comfort, but let's just take a look at that, okay? So we do know we have, and let's just make, we'll say OH in the first run is A, and OH in the second run is B, okay? So if we have, I'm just doing that for simplification on algebra because I do want to demonstrate this for clarity. So we have A to the Y and B to the Y. Well, we can actually just say, we can use our exponent rules. Okay, a lot of times in algebra, we go backwards. We say A to the Y over, or sorry, we say A over B to the Y power on the right-hand side is equal to these 2 things over here. on the left, okay? But we're going to use it for our convenience and sort of put Humpty Dumpty back together again and just say we're going to have a over b to the y power. And that's going to, that's going to be helpful to us because we are actually going to pull our hydroxide concentration from 1 and our hydroxide concentration from run 2, and we'll put it in a nice little mathematical equation down here, okay? And we also pull rates 1 and 2 here. All right, now I did demonstrate here in this example with rate 1 on the numerator, rate 2 on the denominator. Notice here, and I'm going to check mark this equation right here, also right here, okay, that I put rate 2 over rate 1. Why? Because rate 2 is actually bigger. So you end up with a number that's greater than 1. Those are a little bit easier to manage as far as visually spot checking. Okay. Because what do we end up here? When we actually take 26.3 divided by 7.10, I get 3.704. And on the right-hand side, when I take 0.0037 and divide out by 0.0010, I get 3.7. Gosh, they're almost the same. And we know that the power of y, the y value is 1, okay, to make those almost equivalent. Remember, in these problems, you're not going to have exact, you're going to have closeness on these values. They're not going to be exact to the t, but most of us can look at this bottom equation right here. I'll just highlight that in pink or circle it in pink. We know the exponent should be 1. So you would actually do for step 2 the exact same thing, but we're just going to say, hey, okay, we know that the hydroxide concentrations are exact in runs 2 and 3. So those are going to essentially cancel out. And then, of course, the K's cancel out. Those are numerically the same. We don't know what they are. It doesn't matter. They don't give that to us, but it doesn't matter because they will cancel out. And then you're left with just rate 2, rate 3, and then our concentrations of ClO2 here to manage, okay? And we'll apply the same rules of exponents where we can just pull the exponent out and have it sit above that ratio, and we're good to go from a mathematic perspective. Now here on the second step 2, where we're comparing rate 2 and rate 3, we get finally, when we take all of our numbers and divide out, we get 38.44 equals 6.2 to the x power. And we know x would be 2. We know 6 squared is 36. So it would stand to reason that 6.2 squared would be just a little bit above that. So final results are we have an exponent for 2 on the chlorite. Wait, yeah, that is chlorite. Chlorite. Sorry, it's a little bit early on a Sunday morning. And then we know our exponent for OH minus is 1. And that's it for today. Please like and subscribe if you want to follow. I have daily content under the YouTube community post tab, and I like to put out videos from time to time. And I promise I'll be picking those up here in the coming weeks, especially as we approach finals here in May. And I want to thank you again for watching.